In a world driven by data and discovery, one hidden concept continues to challenge how we understand human perception. We begin not in the depths of human consciousness, but across the void of space, where a silent traveler, designated 3I Atlas, once crossed our solar neighborhood. In this first section, let us slowly awaken to the scientific context, how and why the discovery of 3I Atlas matters, and how it connects us to systems beyond our sun. To set the stage, envision a vast darkness pierced by distant stars. We are observers on a small planet, scanning the skies, waiting for anomalies. In the past few decades, astronomers have confirmed that objects can wander between star systems, interstellar visitors. The first, Oumuamua, in 2017. The second, 2I Borisov, in 2019. And now the third, 3I Atlas, first detected in year of detection. Why should we care? Because each of these visitors carries whispers of their origin, clues about how other star systems form, evolve, and eject matter. They are cosmic messengers traveling across light years, arriving at our doorstep. In studying them, we may glimpse architectures and processes very different from our solar systems. In this opening section, we will trace the lineage of interstellar objects, define the term, review the first two, and emphasize why a third is significant in statistical and scientific terms. The calm vastness of space invites wonder, but our tone remains steady, grounded in observable facts. As you listen, imagine slow pans over star fields, distant nebulae, telescopes scanning the skies, and the silence of space. Before 3E Atlas, our understanding of interstellar visitors was limited to two named objects. In 2017, Oumuamua appeared, an elongated, enigmatic object whose origins and nature sparked intense debate. Some saw it as an asteroid, others as a comet with hidden activity, some even speculated non-natural causes. In 2019, 2I Borisov offered a more conventional cometary appearance with gas and dust emissions, confirming that at least some interstellar objects behave like comets. These discoveries reshaped our thinking. They told us that interstellar objects are not mere curiosities. They may be common. The fact that we found two in such short succession suggests there may be many more, passing through the solar system undetected. That opens a new observational frontier. But each discovery came with challenges: limited observation windows, faint signals, uncertain composition, and ambiguous orbits. We learned that detecting an interstellar object requires not only powerful telescopes but also rapid response, careful trajectory calculations, and follow-up observations across multiple wavelengths. So when 3 Atlas was detected, it entered into a lineage of cosmic nomads. The detection itself speaks volumes. Our observational networks have improved, our sensitivity increased, and our readiness to identify anomalies sharpened. In studying 3I Atlas, we can refine what we learned from Oumuamua and Borisov and ask new questions. Is there diversity among interstellar objects? Do they all come from similar processes or from dramatically different environments? In this section, we have connected the first two interstellar objects to the current one, building a foundation of scientific context. The next section will look at how 3I Atlas was discovered, which instruments, surveys, and detection thresholds made it possible. Detection of 3I Atlas required both breadth and depth, sky surveys that scan large areas repeatedly, and sensitive instrumentation capable of detecting faint moving points of light. The Asteroid Terrestrial Impact Last Alert System, ATLAS, is a network designed to spot near-Earth asteroids, but its constant scanning also makes it useful for finding unexpected objects. When an anomalous trajectory was noticed, astronomers swiftly calculated whether it was bound to the Sun or unbound, an interstellar visitor. We will walk through how telescopes process raw images, subtract background stars, identify moving points, and match trajectories. Observers compare positions over time, derive orbital elements, and test whether the orbit is hyperbolic, i.e., unbound to the Sun. In the case of 3I Atlas, the initial orbit solution hinted strongly at a hyperbolic path. The discovery was then corroborated by observatories worldwide. Photometry, spectroscopy, and astrometry each contributed unique data: brightness curves, spectral lines, positional shifts. These observations must be timely, as the object moves quickly, fading as it recedes. The coordination between observational facilities is crucial. In this section, we will trace the timeline of discovery: first detection by Atlas, identification of unusual velocity or trajectory, alerts to global networks, follow-up observations. We will also discuss uncertainties, errors in measurements, perturbations by planets, non-gravitational accelerations, and how these must be accounted for in orbit determination. By the end of this section, listeners will understand the chain of instrumentation, algorithms, and international collaboration that allow us to detect a fleeting interstellar visitor. Next, we will focus on what the data revealed: physical properties, spectral signatures, and hypotheses. Once observations accumulate, astronomers attempt to infer the object's physical nature. For 3I Atlas, we examine brightness variations over time, light curves, color indices, spectral absorption or emission lines, and any non-gravitational accelerations, e.g., outgassing or solar radiation pressure. We explain how brightness variation suggests rotation and shape. If the object's light curve shows periodic fluctuations, that may indicate spin, elongated shape, or surface albedo differences. Comparisons of brightness at different wavelengths hint at composition: silicates, organics, ices, or dust coatings. Spectroscopy may reveal gas emissions or absorption features, letting us test for volatiles like water, carbon monoxide, cyanogen, or dust composition. In prior interstellar objects, 2I Borisov displayed comet-like gas emissions. Oumuamua showed extremely weak or absent gas lines, leading to debates whether it was more asteroidal. In the case of 3I Atlas, we discuss what spectral data was possible. Was there a cometary coma? Did it show gas lines? Was there evidence for dust tails? If so, what kinds of molecules or dust particles? We also explore the possibility of non-gravitational acceleration. If slight thrusts, e.g. outgassing or photon pressure, are present, how do they affect orbit models? This section remains restrained. We report what is known and what remains uncertain. We note error bars, ambiguous detections, and possible biases in observations. For instance, faint objects near observational limits. The aim is to ground expectations in scientific prudence. By the close of this section, listeners should have a clear picture of the physical inferences scientists can draw from distant faint travelers. Next, in Section 5, we reflect on what 3I Atlas's derived properties imply about plausible origin systems. With inferred physical properties, we ask, what kind of system might have ejected 3I Atlas? How common are such ejections? What constraints do we place on other star systems based on one object's arrival? We start by reviewing mechanisms by which material can be ejected from stellar systems: gravitational interactions with giant planets, stellar encounters, or disk instability processes. In a young planetary system with migrating giant planets, dynamic scattering can accelerate planetesimals to escape velocity. In dense stellar clusters, close stellar passages can perturb or eject bodies. We then consider whether 3I Atlas's speed and trajectory hint at certain classes of origin, perhaps a system with large outer planets, or a binary star interaction, or a star in a dense cluster environment. We may even compare to astrophysical simulations. How many ejected bodies does a typical system produce over its lifetime? We also note selection effects. Only objects on certain paths and speeds are likely to reach us, so our sample is biased. The mere fact we detected 3I Atlas suggests a baseline ejection rate among star systems large enough for interstellar wanderers to exist in detectable abundance. Thus, we start building an inverse argument. From one object, we derive constraints on other systems' dynamics, planet populations, and ejection efficiencies. We remain cautious about overgeneralization. As 3I Atlas continues its journey through our solar system, astronomers have carefully tracked its motion and behavior. Unlike typical comets or asteroids, its trajectory is hyperbolic, meaning it is not gravitationally bound to the Sun. This type of path signals an origin from outside our solar system, an interstellar traveler briefly passing through our cosmic neighborhood. Observing its motion allows scientists to estimate not only its velocity but also to infer the forces that may have acted on it over millions of years as it drifted between stars. The object's speed exceeding typical orbital velocities in the solar system hints at an ejection from its parent star system. Such ejections occur when planets interact gravitationally with small bodies, flinging them into interstellar space. By understanding the mechanics of these interactions, we gain insight into how star systems evolve over time, including the processes that shape planetary orbits and the dispersal of minor bodies like asteroids and comets. Spectroscopy has become a critical tool in this process. By analyzing the light reflected from 3I Atlas, astronomers can identify the chemical signatures present on its surface. Early results suggest a composition similar to certain carbon-rich asteroids within our own system, but subtle differences may reveal a unique chemical history. These differences could reflect the conditions of the star system where 3I Atlas formed, such as variations in stellar radiation, temperature, or the availability of volatile compounds during its formation. Observatories around the world, from optical telescopes to radio arrays, collaborate to track such transient visitors. Each measurement refines models of its orbit and composition, building a clearer picture of its nature. Understanding the object's rotation, surface features, and any outgassing events provides clues about its internal structure. For example, variations in brightness over time can indicate irregular shape or surface heterogeneity, both common in small interstellar objects. The discovery of 3I Atlas continues a growing field of research into interstellar interlopers. Each one offers a snapshot of materials from distant star systems, effectively sending back samples across light years. By studying these objects, scientists can compare them to the familiar bodies in our solar system, highlighting similarities and differences that illuminate planetary formation on a galactic scale. In this way, 3I Atlas is more than a fleeting visitor. It is a messenger carrying the chemical and dynamical story of another stellar neighborhood. One of the most intriguing aspects of 3I Atlas is its surface composition. Unlike ordinary comets, which often display strong outgassing as they near the Sun, 3I Atlas shows comparatively muted activity. This subtle difference may indicate a surface layer depleted of volatiles, or perhaps a crust formed from past radiation exposure in interstellar space. Such a crust would insulate the interior, suppressing sublimation and making the object appear less active than typical solar system comets. The measurement of its reflectivity, or albedo, helps constrain its surface characteristics. Early data suggest a moderately dark surface, absorbing more sunlight than icy comets like Halley's or Hale-Bopp. This darkening could result from prolonged cosmic ray exposure over millions of years, gradually transforming organic compounds and silicates on its surface. Studying these changes provides a direct comparison between objects that form and evolve under solar radiation and those exposed to the vast interstellar medium. Thermal modeling plays a complementary role. By estimating how heat penetrates the surface and drives sublimation, scientists can assess whether faint tails or jets might appear as the object nears the Sun. Observations at multiple wavelengths, from visible to infrared, allow researchers to detect even minimal amounts of gas or dust being released. These subtle signals carry valuable information about the molecular composition of the body, revealing whether it contains water, carbon monoxide, or other compounds crucial for understanding chemical diversity in planetary systems. Atlas's shape, rotation, and light curve offer additional clues. Irregular brightness variations suggest it is not spherical, but elongated or lumpy, which is common among small interstellar travelers. These physical characteristics reflect its collisional history, both in its home system and during its journey through interstellar space. Every subtle wobble or variation in speed provides constraints for modeling its internal density and strength. Through these meticulous observations, astronomers are building a multi-dimensional picture of 3I Atlas. Its chemical makeup, rotational behavior, and trajectory collectively inform us about distant planetary systems. By comparing these properties to known solar system bodies, researchers can begin to assess the universality of planet formation processes, understanding whether our own system is typical or an outlier in the galaxy. The motion of 3I Atlas through the solar system offers a rare opportunity to probe the gravitational landscape of our cosmic neighborhood. Unlike objects born within our system, whose orbits often follow predictable ellipses around the Sun, interstellar objects travel on hyperbolic trajectories that are minimally influenced by solar gravity. This allows astronomers to calculate their incoming velocity and direction of origin with high precision. By tracing 3I Atlas's path backward, scientists can estimate which region of the galaxy it likely emerged from, offering indirect clues about distant star systems and the processes shaping their minor bodies. Detailed orbital analysis requires constant observations over weeks or months. Each measurement of position and velocity reduces uncertainties, refining our understanding of its trajectory. Small deviations may indicate gravitational perturbations from planets, solar radiation pressure, or interactions with the solar wind. Even these subtle forces provide insight into how interstellar objects respond to local environments, a phenomenon that is challenging to study in bodies native to our solar system. The orientation of the trajectory also has implications for understanding galactic dynamics. 3I Atlas may carry signatures of its ejection mechanism, whether through planetary scattering, close stellar encounters, or dynamical instabilities in its home system. Each scenario paints a different picture of how star systems form and evolve. For example, an object ejected by a giant planet suggests the presence of massive planetary companions in the parent system, which helps astronomers infer the architecture of distant planetary systems. Furthermore, tracking the object as it moves outward allows for precise predictions of its departure path. Observations during its closest approach reveal its physical response to increasing solar radiation, testing models of thermal evolution in bodies that have spent millions of years in interstellar cold. These data points are essential to compare with simulations of interstellar object dynamics, helping refine our understanding of how these objects survive long-term exposure to deep space conditions. In essence, the study of 3I Atlas's motion connects the microcosm of a small object to the macrocosm of galactic evolution. By carefully recording its trajectory, astronomers are not just tracking a single visitor, they are gathering empirical evidence that illuminates the broader processes shaping planetary systems across the Milky Way. Each calculated curve and observed rotation tells a story of forces acting over light years, offering humanity a brief but profound window into the life of a star system far beyond our own. Spectroscopic studies of 3I Atlas reveal much about its composition and history. By dispersing the reflected light into a spectrum, scientists can identify specific absorption features corresponding to minerals and ices. Early measurements indicate a surface dominated by silicates with traces of carbonaceous compounds, The relative abundance of these materials provides hints about the temperature and chemical environment in its home system during formation. Comparisons with solar system asteroids reveal both similarities and differences. Certain carbon-rich signatures resemble those found in C-type asteroids, while the relative scarcity of volatiles may reflect prolonged exposure to interstellar space. Cosmic rays over millions of years can alter the surface chemistry, producing complex organic molecules and darkening the exterior. Understanding these modifications allows researchers to differentiate between intrinsic composition and alterations caused by the interstellar environment. Infrared observations complement visible light spectroscopy, revealing subtle thermal signatures from the surface. Variations in heat retention and emission indicate surface heterogeneity, possibly caused by uneven distribution of materials or past collisional events. Such variations help scientists model the internal structure of the object, offering insight into density, porosity, and mechanical strength. Studying these compositional features also informs theories about planetary system formation. By comparing interstellar objects to native comets and asteroids, astronomers can assess whether chemical distributions in distant systems mirror those in our solar system or diverge significantly. These comparisons provide empirical data for refining models of planetary formation and migration, highlighting the universality or uniqueness of certain processes. Through careful observation, 3 Atlas becomes a messenger from a distant star, offering a direct chemical snapshot of another system. Each spectral line, thermal variation, and brightness fluctuation contributes to a deeper understanding of the diversity and complexity of planetary systems across the galaxy. The rotation of 3I Atlas provides additional layers of information. Light curves, which measure brightness changes over time, reveal rotational periods and possible shape irregularities. Early analyses suggest a non-spherical shape, likely elongated or lumpy, consistent with expectations for small interstellar objects. These physical characteristics reflect its formation, collisional history, and the stresses experienced during its interstellar journey. Rotational studies are closely linked with compositional observations. Uneven surfaces cause differential heating as sunlight strikes different regions, influencing sublimation rates and possibly leading to minor outgassing events. By correlating brightness variations with spectral data, scientists can detect subtle compositional heterogeneity across the surface. Rotation also affects the stability of the object in transit. Rapid spinning may influence structural integrity, while slower rotation might allow for more stable survival over long interstellar periods. Understanding these dynamics contributes to broader models of how small bodies survive the vast distances between stars without fragmenting or losing significant mass. Moreover, rotation provides a natural laboratory for testing physical theories in microgravity conditions. Unlike terrestrial or near-Earth experiments, interstellar objects experience minimal external influences, allowing pure observation of how rotation interacts with irregular shapes and composition. These insights can inform both planetary science and materials science, bridging observational astronomy with theoretical modeling. By combining rotational, spectral, and trajectory data, astronomers can construct a comprehensive physical profile of 3I Atlas. This multi-dimensional understanding is essential for interpreting the object not as an isolated phenomenon, but as a representative sample of distant planetary processes. Each aspect of its motion and structure adds context to the story of planetary evolution beyond our solar system. Thermal evolution models provide yet another dimension of understanding. As 3I Atlas passes through the inner solar system, it experiences increased solar heating, albeit briefly. By observing changes in emitted infrared radiation, scientists can infer the thermal conductivity and internal structure of the object. These measurements reveal whether heat penetrates deeply, potentially triggering sublimation from ices trapped beneath the surface, or whether a refractory crust prevents significant activity. Infrared observations, combined with rotational studies, allow for mapping temperature variations across the object's surface. Areas exposed to sunlight may warm rapidly, while shaded regions remain cold, creating thermal gradients. These gradients can affect structural integrity, as repeated heating and cooling cycles induce stress fractures over time. Observing such effects in real time offers a unique opportunity to study processes that would normally occur over millions of years, compressed into weeks as the object passes near the Sun. Thermal modeling also informs predictions for potential dust or gas release. Any weak outgassing provides clues about the presence of volatiles and their distribution. Detecting even faint jets would offer direct evidence of internal composition, complementing the data gathered from spectroscopy. By monitoring subtle variations in brightness correlated with thermal activity, astronomers refine models for how interstellar bodies respond to localized heating. In this way, 3I's Atlas serves as a natural experiment in heat transfer, rotation, and surface physics under unique conditions. Observing these phenomena in an object from another star system provides a comparative perspective, enabling scientists to test theories developed from solar system studies in an entirely new context. The object's brief but informative passage allows for real-world testing of models that would otherwise remain theoretical. The trajectory and physical characteristics of 3I Atlas also have implications for understanding the population of interstellar objects in the galaxy. Each detection contributes to statistical models estimating how many such objects travel through interstellar space at any given time. These models inform us about the efficiency of ejection processes in planetary systems and the likelihood of detecting future visitors. By analyzing 3I Atlas in conjunction with previous interstellar visitors, such as Oumuamua and Borisov, astronomers can begin to identify common properties among these objects. Similarities in composition, trajectory, and rotation may indicate generalizable patterns in planetary system dynamics. Differences, on the other hand, reveal the diversity of planetary formation outcomes across the galaxy. Such population studies also carry broader implications for planetary defense. Understanding the frequency and characteristics of interstellar objects helps determine potential risks from high-velocity intruders. Although extremely rare, hyperbolic objects can cross the solar system at speeds far exceeding local bodies, requiring precise modeling for any impact assessments. Ultimately, 3I Atlas adds another piece to the puzzle of galactic planetary dynamics. Its study informs everything from the chemical evolution of star systems to the mechanical processes governing small bodies over interstellar distances. By integrating observational, spectral, rotational, and thermal data, scientists are constructing a holistic portrait of this extraordinary visitor, expanding humanity's understanding of the cosmos in a tangible, data-driven way. Beyond individual properties, 3I Atlas provides insights into the dynamics of planetary system evolution. Interstellar objects like this one are the remnants of complex processes in their home systems. Planetary migration, gravitational scattering, and close encounters between large planets and smaller bodies can result in ejection of asteroids and comets into interstellar space. By studying 3I Atlas, astronomers are essentially examining the outcomes of these distant events. The hyperbolic trajectory of 3I Atlas suggests it was likely ejected by a massive planet, similar to Jupiter or Neptune in our own system. Such planets can impart enough energy to small objects to overcome their star's gravitational pull. Modeling these ejection processes allows scientists to infer properties of planetary systems that are otherwise unobservable. For example, the velocity and direction of 3I Atlas's motion may hint at the orbital configuration of the parent system's planets. Collisions and close encounters in a planetary system leave lasting imprints on small bodies. The elongated, irregular shape of 3I Atlas may be a product of such interactions, combined with billions of years of exposure to cosmic rays and micrometeoroid impacts during its interstellar journey. Understanding these physical changes provides a comparative framework for assessing how common such processes are in other star systems. Moreover, 3I Atlas serves as a case study in the long-term survival of minor bodies in interstellar space. Its structural integrity, preserved despite millions of years of travel, indicates that such objects can endure extreme temperature variations, cosmic radiation, and collisions with interstellar dust. These observations help refine models of planetary system debris evolution, showing how material can persist and disperse across the galaxy. By combining trajectory analysis, rotation, and compositional data, astronomers are uncovering not just the story of 3I Atlas itself, but also a narrative of planetary dynamics in systems light years away. Each characteristic measured contributes to a growing understanding of the frequency and nature of ejection events, the architecture of distant systems, and the survival mechanisms of minor bodies traveling between stars. In this way, 3I Atlas is not merely a visitor to our solar system, it is a messenger delivering empirical data from a distant neighborhood of the galaxy. The chemical composition of 3I Atlas offers a rare window into exoplanetary material. Carbon-rich compounds dominate its surface, accompanied by silicate minerals, suggesting a formation environment with both refractory and volatile materials. These chemical fingerprints hint at processes similar to those that produced small bodies in our own solar system. Yet subtle differences may reflect unique conditions in its home system. Comparative analysis with solar system comets reveals both commonalities and variations. While silicates and organic compounds appear in familiar proportions, the relative scarcity of volatile ices points to a surface processed by cosmic radiation over millions of years. Such processing can transform simple molecules into complex organics, darkening the surface and altering spectral signatures. These changes provide clues to the chemical evolution of matter in interstellar space. Spectroscopy also allows scientists to explore isotopic ratios, which serve as markers of stellar nucleosynthesis. By examining ratios of elements like carbon, nitrogen, and oxygen, researchers can infer the composition of the molecular cloud where 3I Atlas formed. These measurements reveal whether its origin environment was similar to or distinct from our solar neighborhood, offering insights into the diversity of star-forming regions across the Milky Way. Thermal data further enrich this picture. Infrared observations reveal subtle temperature variations across the surface, indicating heterogeneity in composition or surface texture. Such variations may be linked to past outgassing events, collisions, or surface processing, each of which carries a signature of the object's history. By integrating these data with orbital and rotational observations, astronomers can reconstruct a multidimensional portrait of this interstellar traveler. In essence, 3I Atlas acts as a natural sample return mission from another star system. Every chemical signature, thermal anomaly, and physical irregularity contributes to a broader understanding of planetary system formation, evolution, and diversity. By studying it in detail, scientists gain a rare opportunity to examine material from beyond our solar system without leaving Earth, bridging the gap between observational astronomy and comparative planetary science. Rotation-induced effects on 3I Atlas provide additional insights into its internal structure. Variations in light curves suggest a slightly elongated body, with rotational periods affecting how sunlight interacts with the surface. This rotation can amplify thermal stresses, producing small-scale fracturing over time. Understanding these effects informs models of material strength and resilience in minor bodies. The combination of rotation and irregular shape can also influence potential outgassing, even if minimal. Slightly warmer areas may release faint jets of gas or dust, providing information about the distribution of volatiles within the object. These subtle phenomena are crucial for interpreting the thermal and chemical evolution of interstellar bodies, highlighting differences from similar objects within our solar system. Rotation studies also reveal broader evolutionary patterns. Interstellar objects must withstand billions of years of exposure to gravitational perturbations, radiation, and collisions. Observing how 3I Atlas's rotation interacts with its irregular shape helps model survival strategies of minor bodies in interstellar space. This data improves predictions for the structure and lifespan of other hyperbolic visitors, adding statistical weight to our understanding of galactic debris populations. The study of rotational dynamics also complements compositional analysis. Brightness variations linked to rotational cycles help identify surface heterogeneity, correlating areas of darkened carbon-rich material with specific spectral signatures. This integrated approach provides a detailed, multi-dimensional view of the object, combining physical, chemical, and dynamical properties into a coherent narrative of interstellar survival. Ultimately, rotation serves as both a diagnostic tool and a storytelling device. It allows astronomers to infer the mechanical history, surface composition, and potential evolutionary path of 3I Atlas, linking its current state to its origin in a distant star system. Each measured wobble or brightness fluctuation conveys information from across light years, creating a bridge between observational astronomy and theoretical modeling of interstellar processes. The study of 3I Atlas is not limited to a single observational method. Multi-wavelength approaches spanning visible, infrared, and radio frequencies provide complementary insights into its nature. Each wavelength probes a different physical or chemical property, offering a comprehensive understanding of the object's composition and behavior. Visible light observations track brightness variations, rotation, and potential shape irregularities, forming the basis for dynamic modeling. Infrared data reveal thermal emission and surface heterogeneity, critical for understanding heat retention and potential sublimation processes. Radio observations, though more challenging, can detect faint emissions from gases or interactions with the solar wind, further enriching the dataset. Combining these observational channels enables scientists to construct a holistic picture of 3I Atlas. The interplay of thermal, rotational, and compositional data allows researchers to model its internal structure and evolutionary history with unprecedented detail. This multifaceted approach is particularly valuable for interstellar objects, which are rare and fleeting, offering only brief windows of observation. Moreover, the integration of data across wavelengths aids in refining models of interstellar object populations. By comparing observed properties of 3I Atlas with simulations of ejected bodies, astronomers can estimate the frequency, size distribution, and compositional diversity of hyperbolic objects in the galaxy. These insights contribute to a broader understanding of planetary system evolution and galactic chemical dynamics. Ultimately, multi-wavelength studies exemplify the depth and precision of modern astronomy. They demonstrate how the convergence of observational techniques can extract detailed knowledge from brief, transient visitors like 3I Atlas. Each dataset enriches the narrative, turning a distant interstellar traveler into a well-characterized source of scientific insight. Interstellar objects such as 3I Atlas also inform our understanding of cosmic chemical diversity. The specific combination of silicates, carbonaceous compounds, and potential traces of volatiles provides a snapshot of the molecular environments in other star systems. Comparing these compositions with solar system analogs allows scientists to evaluate whether certain chemical patterns are universal or context-dependent. Isotopic studies, though challenging for distant visitors, offer additional clues. Ratios of stable isotopes can indicate the type of stellar environment in which the object formed, reflecting variations in nucleosynthesis across the galaxy. These markers help identify the likely age and origin of the body, linking it to broader galactic chemical evolution. Observations of 3I Atlas's surface and thermal characteristics complement these chemical studies. Subtle variations in brightness and temperature suggest heterogeneous distribution of materials, possibly shaped by past collisions, radiation exposure, or minor outgassing. Each feature contributes to an integrated understanding of the object's history, revealing the interplay of mechanical, thermal, and chemical processes across millions of years. Studying interstellar objects also has implications for planetary system formation theories. The presence or absence of volatiles, the ratios of silicates and organics, and the degree of surface processing inform models of disk chemistry and planetary migration. These data points allow scientists to refine simulations of how star systems produce and eject minor bodies, offering a rare empirical reference for testing theoretical frameworks. In this way, 3I Atlas becomes more than a fleeting visitor. It is a messenger carrying empirical evidence of processes beyond the solar system. Its study bridges observational astronomy, planetary science, and galactic chemical evolution, providing a multidimensional perspective on how stars, planets, and minor bodies form, evolve, and interact across the Milky Way. The trajectory of 3I Atlas also provides insight into interstellar travel distances and the timescales over which such objects traverse the galaxy. Given its hyperbolic speed relative to the Sun, this object likely traveled for millions of years before reaching our solar system. These immense timescales offer a perspective on the endurance of minor bodies in the cold, radiation-filled expanse of interstellar space. Its prolonged journey exposes 3I Atlas to cosmic rays, micrometeoroid impacts, and interstellar dust, gradually altering surface chemistry and texture. The observed darkened surface reflects these cumulative effects, providing a natural record of interstellar exposure. By studying these features, scientists gain indirect insight into the conditions and hazards that small bodies face beyond their parent systems. The velocity and direction of 3I Atlas also suggest the dynamical mechanisms by which objects are ejected from their home systems. Close encounters with giant planets can impart sufficient energy for ejection, while stellar perturbations in dense star-forming regions may accelerate minor bodies to escape velocity. Analyzing its current motion allows astronomers to reverse engineer these processes, building models of planetary system dynamics and debris dispersal. Furthermore, understanding these trajectories informs detection strategies for future interstellar visitors. Objects traveling at high speeds spend only brief periods near the Sun, making timely identification and observation essential. Data from 3I Atlas help refine orbital prediction algorithms, enhancing the efficiency of surveys designed to capture these rare, fleeting phenomena. Ultimately, the motion of 3I Atlas is a living archive of interstellar dynamics. By studying its path, scientists trace not only its individual history but also the broader processes shaping the galaxy's population of minor bodies. Each calculated orbit and velocity vector adds to our understanding of the complex interplay between stars, planets, and the interstellar medium. The structural integrity of 3I Atlas is another area of scientific interest. Despite traveling through interstellar space for millions of years, the object remains intact, suggesting a surprisingly robust internal structure. Understanding how small bodies maintain cohesion under extreme conditions informs both planetary science and materials science. Observational data indicate that 3I Atlas may be composed of a mixture of silicate and carbonaceous materials with porosity that allows it to absorb minor impacts without disintegration. Its elongated, irregular shape is typical of small collisionally processed bodies, suggesting a history of past impacts or close encounters with other minor objects in its home system. The study of structural properties also provides insight into the survival mechanisms of interstellar objects. Thermal cycling, cosmic ray exposure, and micrometeoroid bombardment all present challenges to long-term integrity. By observing how 3I Atlas responds to solar heating during its brief passage, scientists can infer the distribution of mass and the mechanical strength of its interior. Understanding structure has further implications for interpreting observational data. Light curves, rotational dynamics, and thermal emissions all depend on shape and internal composition. Integrating these measurements allows researchers to create three-dimensional models of the object, linking surface observations with deeper internal properties. In this sense, 3I Atlas serves as a natural laboratory for studying the mechanics of interstellar survival. Its continued cohesion demonstrates that small bodies can endure extreme conditions over vast distances, providing empirical validation for theoretical models of long-term interstellar durability. Surface heterogeneity offers additional clues about the history and evolution of 3I Atlas. Variations in reflectivity, color, and thermal properties indicate uneven distribution of materials across its surface. These differences may result from differential radiation exposure, micro-impacts, or historical outgassing events in its home system. Spectral studies help identify specific minerals and organics associated with these surface variations. Certain regions may contain higher concentrations of carbonaceous material, while others are dominated by silicates. Mapping these differences allows astronomers to connect physical appearance with chemical composition, revealing the processes that have shaped the object over millions of years. Thermal imaging further enhances this understanding. Subtle temperature differences highlight surface irregularities and variations in heat absorption. These observations inform models of thermal conductivity and help estimate how heat penetrates into the interior, providing context for potential sublimation or structural changes during its solar system passage. By integrating structural, compositional, and thermal data, scientists can construct a multidimensional portrait of 3I Atlas. This holistic approach reveals not only its current state, but also the cumulative effects of interstellar exposure, collisions, and rotational dynamics, offering a comprehensive understanding of minor bodies traveling between stars. Ultimately, surface heterogeneity emphasizes the complexity and diversity of interstellar objects. Each variation is a record of past events, environmental conditions, and chemical evolution, contributing to our broader understanding of planetary system diversity and the resilience of minor bodies across the galaxy. The study of 3I Atlas's trajectory and properties also informs our understanding of galactic population dynamics. Each interstellar object represents a statistical data point, providing evidence for the frequency and characteristics of ejected minor bodies. Combining observations from multiple interstellar visitors allows astronomers to refine models of star system evolution, planetary ejection mechanisms, and the distribution of material across the Milky Way. By comparing properties such as size, shape, rotation, and composition, scientists can identify trends and anomalies. For instance, similarities in carbon-rich surfaces among interstellar objects may indicate a commonality in formation environments or evolutionary processes, while differences reveal the diversity of planetary system outcomes. Trajectory analysis also provides insight into the gravitational influences of nearby stars and galactic structures. Small deviations from predicted hyperbolic paths can indicate past encounters with stellar or interstellar matter, offering indirect evidence of the density and dynamics of the local galactic neighborhood. Population studies have practical implications as well. Understanding the frequency and distribution of interstellar objects aids in the design of detection systems and informs risk assessments for potential high-velocity intruders. While impacts from such objects are extremely rare, accurate modeling enhances our preparedness and expands our scientific understanding simultaneously. Ultimately, each interstellar visitor, including 3I Atlas, contributes to a growing galactic census. The combination of physical, chemical, and dynamical data builds a more complete picture of how planetary systems distribute material beyond their borders, revealing patterns of universality and diversity across the Milky Way. The detection of 3I Atlas has spurred advancements in observational techniques. High-cadence surveys and wide-field telescopes play a critical role in identifying transient interstellar visitors. Rapid follow-up observations across multiple wavelengths are essential to capture compositional, rotational, and thermal information before the object recedes into deep space. The collaborative effort between observatories worldwide highlights the interdisciplinary nature of modern astronomy. Optical telescopes provide high-resolution imagery and light curves, infrared instruments track thermal behavior, and radio arrays offer potential detection of gas or dust emissions. Combining these resources creates a comprehensive dataset that captures the fleeting opportunity presented by 3I Atlas. Detection technologies are also evolving in response to interstellar object studies. Improved sensitivity, automated identification algorithms, and real-time data analysis enhance the likelihood of discovering future hyperbolic visitors. Lessons learned from 3I Atlas will inform survey strategies for years to come, enabling astronomers to detect fainter, smaller, or faster-moving interstellar bodies. Furthermore, studying these objects encourages theoretical refinement. Observations of trajectory, composition, and structural properties feed back into models of planetary system dynamics, ejection processes, and interstellar survival. Each discovery strengthens the predictive framework for both galactic evolution and minor body behavior. Through 3I Atlas, science gains not only specific knowledge about a single interstellar object, but also broader insights into the methodologies, technologies, and collaborative approaches necessary to study the transient, distant, and otherwise inaccessible components of our galaxy. The comparative analysis of interstellar objects like 3I Atlas and its predecessors provides a broader context for understanding planetary system formation across the galaxy. By examining physical, chemical, and dynamical characteristics, scientists can identify patterns and variations among objects originating from different star systems. These comparisons reveal the diversity of formation environments, highlighting both similarities and deviations from the conditions observed in our own solar system. For example, the elongated, irregular shape of 3I Atlas, coupled with its surface composition, suggests that certain structural and chemical features may be common among ejected minor bodies. Meanwhile, variations in volatile content and thermal behavior illustrate how individual formation histories and interstellar exposure contribute to unique evolutionary paths. By studying multiple interstellar visitors, astronomers can begin to quantify these trends, providing insight into the frequency of specific processes such as planetary scattering, collisional evolution, and cosmic ray processing. Additionally, comparative studies offer clues about the architecture of distant star systems. The hyperbolic velocities of interstellar objects carry imprints of the gravitational interactions that ejected them, indirectly revealing the presence of massive planets or dense stellar environments. Analyzing these trajectories in combination with compositional data creates a multi-dimensional understanding of planetary system diversity, enriching models of galactic evolution and material exchange between systems. The interdisciplinary nature of this research is also noteworthy. Observational astronomy, spectroscopy, thermal modeling, and orbital mechanics converge to create a cohesive picture of interstellar objects. Each dataset contributes a piece of the puzzle, allowing researchers to reconstruct formation environments, dynamical histories, and long-term evolutionary processes. This integrative approach underscores the value of studying 3I Atlas not as an isolated phenomenon, but as part of a growing collection of interstellar messengers carrying information from across the galaxy. Ultimately, comparative analysis transforms 3I Atlas from a single, fleeting visitor into a data point with galactic significance. By situating its properties within the broader population of interstellar objects, scientists gain insight into universal patterns, variations, and the fundamental mechanisms that shape planetary systems beyond our solar system. Looking ahead, the study of 3I Atlas emphasizes the importance of preparedness for future interstellar discoveries. Each new object presents an opportunity to expand our knowledge of planetary formation, chemical diversity, and galactic dynamics. Rapid identification and observation are crucial, as these visitors spend only brief periods within observational range before returning to interstellar space. Advances in telescope sensitivity, automated detection algorithms, and coordinated global observation networks are making it increasingly possible to capture data on these rare phenomena. Surveys such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time (LSST) are expected to identify additional hyperbolic objects, providing opportunities for comparative analysis and statistical studies. In addition to observational readiness, theoretical modeling continues to evolve. Simulations of ejection mechanisms, interstellar survival, and surface processing help predict the characteristics of future interstellar objects, guiding observation priorities and informing instrument design. By combining real-time data with predictive modeling, astronomers can maximize the scientific yield from these transient visitors. Furthermore, interdisciplinary collaboration will remain essential. Chemistry, physics, planetary science, and astronomy intersect in the study of interstellar objects. Insights from each field enhance interpretation of observational data, allowing researchers to reconstruct formation histories, chemical evolution, and dynamic trajectories. 3I Atlas exemplifies the potential of this integrated approach, serving as a template for studying future visitors. Ultimately, the continued study of interstellar objects extends humanity's understanding of the galaxy. Each discovery, including 3I Atlas, adds to a growing archive of empirical knowledge, enabling scientists to explore the chemical, structural, and dynamical diversity of planetary systems beyond our own. This research not only illuminates distant star systems but also enriches our understanding of the processes that shaped our solar system and the broader Milky Way. The significance of 3I Atlas lies not only in its transient presence but in the lasting scientific legacy it leaves. Observations of its trajectory, composition, rotation, and surface characteristics provide a multidimensional view of a small body from another star system, offering empirical evidence of processes occurring far beyond our observational reach. Each aspect of 3I Atlas contributes to a broader understanding of galactic planetary system dynamics. Its chemical composition reveals the molecular environment of its origin, while rotational and structural properties shed light on collisional history and interstellar survival mechanisms. Trajectory analysis informs models of ejection, planetary scattering, and the distribution of minor bodies throughout the galaxy. Beyond immediate observations, 3E Atlas establishes a benchmark for future interstellar object studies. By integrating data from multiple wavelengths, rotational light curves, thermal profiles, and spectroscopic signatures, scientists can develop comprehensive models of interstellar material and survival dynamics. These models enhance predictions for future discoveries, guiding both observational campaigns and theoretical simulations. Moreover, the study of 3I Atlas highlights the interconnectedness of planetary science, astronomy, and galactic evolution. Each measured property informs a chain of inference, connecting distant chemical and dynamical processes to the observations we can make from Earth. The object's brief passage serves as a messenger from its home system, allowing humanity to extend its understanding of planetary formation, chemical diversity, and interstellar dynamics without leaving the solar system. In conclusion, 3I Atlas represents more than a rare visitor. It embodies the potential of interstellar exploration through observation. Its study enriches our understanding of the universe, providing empirical data on processes shaping distant star systems, and serves as a foundation for future research on interstellar objects. Each measurement, each spectral line, and each calculated trajectory contributes to a collective understanding of our place in the galaxy, linking the fleeting presence of a distant object to enduring knowledge about the cosmos